Yes.
Okay. Hello. Thank you for the invitation. So I have a question about the talk. So what is the level of the audience? Should I start from the basics, or should I expect that people are
It
familiar
depends
with
on the basics of what, because well, it's complexity seminar.
Okay.
But
So what tensors are, what algebraic circuits are, and how to transform algebraic circuits.
well, if you remind me what do you want from tensors, that would be fine.
Okay. So maybe I should start a little bit from what tensors are and why do we need them in complexity theory. So when we talk about tensors, we usually say that if you know what tensors are, just think about them as like three-dimensional matrices or trilinear forms. And essentially, what we mean is if you have a matrix, for example, so if you have a matrix, usual matrix, we say that this matrix defines a linear map by multiplication, matrix vector multiplication. So if you have yi is the sum of aij x j, then this is a linear map. And if this matrix is, well, let's say of size m times n, then this map is from n vectors to m vectors. But using this matrix, we can also define the adjoint map, which is also linear, but goes in the opposite direction, essentially by row vectors. And we can also consider the bilinear form, J, which is y bilinear from Cn times Cm to C. And essentially, the thing is that we can freely go from one of these maps to another because they're defined by the same matrix. So if you have, for example, a map F, we can say that we can define phi of xy as inner product fx I, yi, and so on. And in the same way, we can define tensors as three-way array of scalars. So let's say we have this box of complex numbers of size L times N times N. And this box of scalars can be used to define either a linear map, for example, from CL to CM times N. So Fx is Y, some matrix, and Yjk is again the sum of for all I is I. Or we can use it to define a bilinear map, which takes two arguments. Phi of xy is z if zk is sum of tijk xi yj. Or we can use it to define a trilinear map, let's say psi, which is also defined by this set of coefficients. And again, if you have a bilinear map, if for some reason it's more convenient to use a trilinear map in this place, we can just go from one of this representation to another, or we can actually define three different linear maps from each of the factors here. And again, because the numbers are the same, we can essentially say a tensor is something that can be used as a linear map or a bilinear map or a trilinear map. And in particular, if we study complexity theory of bilinear maps, it is often convenient to forget like which indices corresponds to input and which index corresponds to output, is just treat them as the same. So let's say we have bilinear map, bilinear, and we say it corresponds to a tensor which is a trilinear form, x, y, z, which is essentially a scalar product of x, y times z. Now, so the computational problem is we want to compute the value of this bilinear map phi on given input x and y. And we want to compute it using algebraic circuits. So algebraic circuits are circuits, so directed cyclic graph and so on. So the inputs are coordinates of x or coordinates of y. And the gates are addition, multiplication, and we also use a gate which multiplies by some constant. So for example, times 2 or times 3, because it's usually more convenient to analyze linear operations, so addition and constant multiplication, separately from like proper non-linear multiplication. And if a circuit C computes phi, then we can actually transform it in a very nice way, which is nice to analyze algebraically. Namely, we can say that there exists a circuit C prime of the following form. So we have here the inputs of x. We feed them to some linear map A. Linear. So it only contains additions and constant multiplications. And we have the same for y. So these linear maps have some number of outputs. And then we do coordinate-wise multiplication of these outputs. And after we did these nonlinear multiplications, we apply again some linear post-processing. And this transformation doesn't blow up the circuit much with, so it has at most twice a number of multiplications. And at most 3 times number of gates total.
And this is true only for bilinear functions, or
well, this can be stated generally, and this blow up grows with a degree. This is the general result of Strassense.
But you state only for bilinear.
Essentially, how it's done is at each point we compute some polynomial, and when we transform the circuit, and each gate we track the part of polynomial which is linear in x, a part which is linear in y, and a part which is bilinear. And then, for example, if we have an addition gate and inputs f and g have form f1 of x plus f2 of y plus f3 of xy, and for G is the same, we can just replace this addition gate by 3 addition gates for F1, F2, and F3. F1, G1, F2, G2, F3, G3. And for the multiplication gate, again, if we have a multiplication gate, which is F and G, and F is F1 of X plus F2 of Y plus F3 of X, Y bilinear. And we can replace this multiplication gate by the following instruction. We only need to multiply F1 by G2 to get the bilinear part of this multiplication. And we also need to multiply F2 by G1. And we add them to get the bilinear part of the result. And the linear part will be non-existent. That's essentially the proof. It's a special case of a general result by Strassense. And
maybe I not understand. What's happened with F3 and G3?
So because, so here, because I don't allow constant inputs, if we have a multiplication and there is F3 and G3, they're multiplied. So here there's some part of degree 4. But because our output is a bilinear map, it should cancel somewhere. So it doesn't matter that we don't track it.
Right, I see.
So we have this special kind of circuits which are called a bilinear circuit. Bilinear circuit for phi. We have X. It has some linear pre-processing of X and Y. And we have some multiplications. And then we have linear post-processing by some block C. And suppose we want to count, so let's say the complexity is the number of multiplication gates. And we have a nice algebraic representation. So in this case, so phi of xy is so here after the linear block A, we compute some linear forms A1 of x up to AK of x, where K is the number of multiplication here. And on the right, we also compute some B1 of y up to BK of y. Then we have some product, and we do some linear combinations of products AI of x times BI of y. And essentially, this linear map C shows us how to put these products into different coordinates of the output. So we have sum of I from 1 to k, these products, A1 of x times BI of y, times some vectors CY, which shows how to redistribute these products to the output. And if you look at this in the trilinear form, then the trilinear form would be essentially the same, except that we have the product of 3 linear components here. So we can define the complexity notion for tensors, so tensor rank. So the rank of T is the minimal possible R such that T can be represented in the form of this sum with R summed. And we can also define a notion of reduction for our complexity theory. So if we have some circuit which can compute a bilinear map phi, we say that some other bilinear map psi reduces to phi if we can compute psi by applying again some linear pre-processing and post-processing to phi. And so this means that psi of xy is phi of ax and by times c. And if phi corresponds to a trilinear form T and psi corresponds to a trilinear form S, then S of x, y, and z is T of ax, by, and c dual z. And from this we get the definition. So one tensor is a restriction of another. S is a restriction of T if there exists some linear map A, B, C such that S of x, y, z is T of ax, by, and cz. And if these maps are invertible, so we can get from T to S, reduce computationally, and also computationally reduce from S to T, then we call S and T are equivalent or isomorphic. And now we can actually phrase all statements about complexity of linear maps, of bilinear maps, in terms of reductions, because we can define the diagonal tensor In, which as a trilinear map looks like this. It's the sum of n summons, each of which is the product of corresponding coordinates. And if you look at it as a bilinear map, it means that that I is a product of coordinate-wise product of vectors x and y. So it corresponds to this coordinate-wise multiplication block inside of a bilinear form, and this block actually computes a diagonal tensor of size equal to the number of multiplication. So tensor is a restriction of In if and only if the rank, so I don't remember. So the rank of a tensor I will denote by R of T is less than n if and only if there exists a bilinear circuit for phi T with n multiplications. So now we have a notion of complexity and the notion of reduction. And the most important bilinear map, which we actually want to compute, is matrix multiplication. So let's say I will denote it by M, L, N. It is a tensor. Sorry. It takes 3 matrices and gives us a sum. I goes to L, J goes to M, and K goes to N. Xij, Yjk, Zki. This is, as a training map, is a trace of product of 3 matrices. And as a bilinear map, it's product of 2 matrices, except with the transpose, because we swapped the indices here. But of course, transpose is an invertible operation, so it's actually equivalent to the matrix multiplication. So, for example, if you know the Strassense algorithm, Strassense algorithms work essentially in the following way. First, we construct a bilinear algorithm for 2 by 2 matrix multiplication. So we have the tensor M2, 2, 2, and we construct a bilinear algorithm, or essentially a reduction from I7. So we have 7 multiplication to compute product of matrices of size 2 by 2. And then we use the fact that block matrices can be multiplied in the same way as usual matrices. So we can then use this algorithm to multiply block matrices and analyze the complexity and get that the rank of 2 to the k matrix multiplication is at most 7 to the k. Or for arbitrary size, it would be O to the n to the log of 7. And here we use this nice property of matrix multiplication that block matrices can be multiplied the same way as scalar matrices. And in tensor language, it's usually given by Kronecker products. So if you have 2 tensors, which in coordinates are given by some t, I, j, k, and s, I prime, j prime, k prime, we can form a tensor product, a Kronecker product of t and s, in the same way we form the Kronecker product of 2 matrices. This is tensor which is indexed, so it's of size, if this is L by M by N tensor, and this is a L prime by M prime by N prime tensor, and it has size L L prime times M M prime times N N prime. And elements of the coordinates of the tensors are indexed by pairs I prime, G prime, K prime. And what we do is we multiply the coordinates of t by the coordinates of s. So this is a construction which is somewhat strange to interpret directly, but essentially what it says is that this Kronecker product corresponds to a map which has some kind of outer structure and some kind of inner structure. So, for example, if T is computed by some bilinear circuit, then we can construct a circuit for T tensor S in the following way. So inputs of T tensor S come in blocks. So for example, if T has 3 inputs and S has, for example, 4 inputs for X, then T tensor S has 3 blocks by 4 inputs. And when we do the linear part, we apply this linear map to corresponding inputs in each block. So in the end, the linear map would be the Kronecker product of A times the identity matrix. And the output will also contain some blocks. The same would be for B. And when we combine these blocks of variables, we use this tensor S to work in the inner structure. And then, of course, again, some linear post-processing by C. And there's the identity, so it's block-wise processing. So the Kronecker products have this form. They have some outer structure which is processed by the tensor T, and they have some inner structure which is processed by the tensor S. For example, matrix multiplication, block matrix multiplication. Block matrix is consists of blocks, and the outer structure is that we can multiply block matrices by multiplying blocks in the usual way. And the inner structure is that when we already take 2 blocks and multiply them, we use the usual matrix multiplication. And so this block matrix multiplication can be stated in the tensor language as the following statement. So if we we take the Kronecker product of 2 matrix multiplication tensor, we get something which is equivalent to a larger matrix multiplication tensor. And in particular, if you take the tensor powers, let's say K, we get a large matrix multiplication tensor. And the thing is, the restrictions behave well with respect to this Kronecker product. So if T is a restriction, if T prime is a restriction of T, S prime is a restriction of S, then Kronecker of T prime and S prime is a restriction of T Kronecker S. And thus, this is essentially how Strassense algorithm work. So we have M222 is a restriction of I7, and it follows that M2 to the K, 2 to the K, 2 to the K, which is a Kronecker power is a restriction of I7 to the k, which is also diagonal tensor of size 7 to the k. And thing is, now we can actually state something not only for multiplications, but also for a total number of operations. So if some tensor is a restriction of In, then total number of gates needed to compute T tensor power of k is O of n to the k. Maybe times some logarithmic factors. And this is in essence how all the matrix multiplication algorithms work. They construct some bilinear algorithms for small matrix multiplication and amplify it to give an upper bound for large matrix multiplication. So yeah, so if matrix multiplication tensor of size n times n is a restriction of a diagonal tensor M, then we can multiply n times n matrices can be multiplied using n to the log m base n arithmetic operations. And the optimal number that we can put here is called the exponent of matrix multiplication. And so the omega, we can define it as an infimum of log n times m, such that m and n is a restriction of m. And this is essentially how we use tensor language in matrix multiplication algorithms. Now, first algorithms like Strassense and Pan, they gave this kind of explicit construction for a bilinear circuit, essentially. But the more involved constructions, such as Schoenhage's algorithm and Coppersmith-Winograd method, they use different constructions. They use some intermediate tensors. So how does the Coppersmith-Winograd algorithm for matrix multiplication works on a high level? We have some intermediate tensor T, and this tensor is chosen so it has some nice algebraic structure, and this algebraic structure can be used to construct explicit algorithms for T. So high tensor powers of T have explicit restrictions from some diagonal tensors, which I will write here as follows. So let's say we have this kind of restrictions between tensors. And it also has nice combinatorial structure, which allows us to extract matrix multiplication from it. So this is in Coppersmith-Vinograd's paper, which is called Matrix Multiplication Using Arithmetic Progressions, they use some Salem-Spencer sets to find explicit restrictions from T, from some high tensor powers of T to matrix multiplications, which I will write here. Like we have 2 by 2 by 2 matrix multiplication, which also has some tensor power minus O over K. And this means that M222 tensor of K is a restriction of I2 tensor P over QK plus O of K. And if we take logarithms, we say that omega is less than P over Q. So this is how we use tensors for matrix multiplication in a very general level. Now, how to prove lower bounds? So as we see, the algorithms for matrix multiplication corresponds to restrictions between powers of matrix multiplication tensor and powers of diagonal tensor. So if we have this kind of relation, then omega is less than P. And how to prove that this kind of restriction doesn't exist? Suppose we have a map from tensors to real numbers, let's say positive real numbers, which has the following properties. So it's monotone with respect to tensor restrictions. And it's also power multiplicative. Then we can use this map to get some abstractions for this, getting restrictions between tensors. So if you have a restriction of this form, then f, the value of our function f on matrix multiplication tensor is bounded by the value of f on the diagonal tensor in the following way. And if we take power 1 over k, this means that fi2 to the power p. So p is at least log f on the matrix multiplication tensor over log f on the diagonal tensor. And this is lower bound for matrix multiplication. This was essentially, well, the idea is, of course, not that complicated, but it was stated, I think, first by Strassen in '86, where he found at least some maps which have this property. And he also proved that if we actually find all the possible maps F which have this property, so omega is actually the minimum. Yeah, the minimum maximum over all maps F which have our properties of log F on matrix multiplication tensor, log F on the diagonal tensor. The problem is these kinds of map are very hard to construct, and even after we construct them, they are very hard to compute. So the Strassense introduced maps which he called support functionals. And support functionals have nice properties, but only for a subclass of tensors. A subclass of tensors, which are called oblique tensors, and they are defined in the following way. So Tijk. In some basis, Ijk, the set of all indices such that the coordinates are non-zero is an anti-chain in the partial order, which is defined by some order on each individual index. And only another way to construct these functions, if we have some functions, for example, rank has this property that if you take a Kronecker power, then the rank of Kronecker product is at most the product of ranks of factors. And then there exists limit of this expression, which we denote like this. This is called asymptotic rank. And this asymptotic rank actually fulfills all the properties that we need. And this way we can define asymptotic versions of any tensor functional which satisfies either supermultiplicative property or submultiplicative property. But this kind of functionals are actually not easy to compute usually. And in 2016, well, in 2015, I think there were some results on progression-free sets and cup sets and combinatorics. And in 2016, Terence Tao constructed, essentially he cast these results in a tensor language, and he constructed a function which called slice rank. It is a version of a rank of tensor. So the usual rank of a tensor, as we said, is a minimum R, such that tensor can be expressed as a sum of R summands, each of which is a product of 3 linear form. And the sliced rank is a modification of this definition. We have also some elementary summands, which now can take the following form. Either we have A of X times B of YZ, or A of Y times B of XZ, or A of Z times B of XY. Now, and this slice rank can also be used in this construction, which gives us a nice function of tensors that we want. And these functions actually can be computed for, again, for some class of tensors. So for oblique tensors, this asymptotic slice rank of T can be computed. In the following way. So slice rank of T is actually maximum of minimum of 2 to the H1 H of P1, 2 to the H of P2, 2 to the H of P3, where P is a probability distribution on the set where Tijk is not 0, and P1, P2, and P3 are marginal distributions. And this actually is not very hard to prove. So if you have a tensor T, which is given by Tijk, I change that key, then its high Kronecker power would be given as follows. So we have some sequences ijk, sequences of k indices, and here we have a product of is, gs, ks. S is from 1 to k. Here we have products of xis, product of yjs, product of zks. And all these sequences we can separate by type. So if I have a sequence I, for example, is a sequence of indices, k indices, it corresponds to the probability distribution. So probability that is equal to I is a probability distribution. So we can separate all sequences by the probability distribution, and in this way, this large tensor t to the power of k, which is a box of numbers, can be structured as a sum of smaller tensors, each of which corresponds to one to a triple of probability distributions. T, P1, P2, P3. And this T, P1, P2, P3 is non-zero if and only if there is a probability distribution on the support of the tensor, on the set of all where all the T, I, J, K are non-zero, probability distribution with marginals P1, P2, P3. And the size of this block, so T, P1, P2, P3, has size which is given by the multinomial coefficient. So the number of all sequences which have the same distribution of elements in them is a multinomial coefficient, and the size is approximately this 2 to the entropy times k. So approximately this is 2 to the h of p1 times k times h of p2 times k times h of p3 times k. So if we take all the non-zero blocks, and each of these blocks we can decompose by slices simply by taking the first coordinate as a of x, for example, and the rest is an arbitrary bilinear form. Or the second or the third one. So we have here 3 different variants, and we choose the optimal of them. And then we get that slice rank of t to the power of k is less than some polynomial in k, which is the number of all possible probability distributions, times this minimum. P3. And when we take the root of this, then this polynomial part goes to 1, and here we have k's power, and we get exactly this. Was this somewhat understandable?
Sort of.
Okay.
Sort of.
So, okay. And how much time do we have actually?
So we spent 1 hour, so we can have, yeah.
Okay. So what we did is we defined a different quantity, which is slice rank, which is we call weighted slice rank. So let's say xi is a triple of numbers such that maximum of these three numbers is 1. I denote the slice rank, the weighted slice rank with index xi as the minimal possible sum R1 1 over xi1 plus R2 1 over xi2 plus R3 1 over xi3, such that, again, T has the same kind of, has a slice decomposition. With R1 summands of the form A of x times B of yz, R2 summands A of y, B of x, z, R3 summands A of z times B of xy. And again, we define the asymptotic variant of this rank as this kind of thing. And we were able to prove a similar statement for this kind of slice rank. We proved actually two things. We proved something for tensors over complex numbers. This slice rank xi is a maximum, again, of minimum of 2 to the h of p1 over xi1, 2 to the h of p2 xi2, 2 to the h of p3 over xi3. Over all p1, p2, p3, which are probability distribution in something which is called the moment polytope of a tensor. So it's something which is defined using representation theory. Let's say pi of t. This is a moment polytope. And this is related to quantum functionals, which were recently introduced by Christian Vrane and Zuidam. They extend Strassense result from oblique tensors to all tensors over complex numbers. The problem is this kind of representation theory only works over complex numbers. And slice rank has many applications in combinatorics where it's very important to work over finite fields. So this kind of things is useful, but not in all situations. We also prove the same thing, essentially the same thing, but now two marginals of probability distributions on the support. The support is a set of all indices where t is non-zero. And this we prove, again, for a specific class of tensors, not for all tensors, but actually for slightly less class of tensors than the previous results of Strassense and tau. And this thing is, again, we prove this using invariant theory, and this kind of invariant theory only work for a specific class of tensors, which are called tight tensors. Tight tensors are defined as follows. So if Tijk is non-zero, then I plus j plus k must be some kind of constant some constant c. So all the non-zero coefficients are contained on some plane, essentially in this box of numbers. And again, if we take a high tensor power of k and decompose it into blocks with different probability distributions, the first thing we prove is that these blocks are what's called semi-simple tensor. So the tensor S is semi-simple if not semi-simple, semi-stable. Sorry. Semi-stable. If you look at the orbit of this tensor AX, so if we apply all the linear maps, but now we say that these linear maps must have determinant 1. So they lie in this special linear group. Let's say, for example, our tensor is n times n times n for simplicity. N. If the closure of the orbit doesn't contain 0. So essentially S is not semi-stable if there exists a sequence A of t, B of t, C of t, which have determinant 0, such that limit S of A of t x, B of t y, C of t z is 0 for all x, y, z. And the first thing to prove is that these blocks will be semi-stable tensor. We use a result from geometric invariant theory from the paper of Kempf, instability in invariant theory. And then we prove that actually if a tensor has low weighted slice rank, then it is not semi-stable. So let's look at how this works. So let's say T is a sum of R1 summands of one kind plus R2 summands of second kind y x z plus R3 summands of the third kind. Now, all these linear forms A we can assume are linearly independent, because if there is something, some A which can be expressed through other forms A, we can just redistribute the summands and say that all the A's are now linearly independent. So after a change of basis, we can actually assume that these A's are first basis linear forms. These A's are also first basis linear forms. So T actually has the following form. So T ijk is 0 if I greater than R1, G greater than R2, and K greater than R3. This means in the first direction, we have some R3 summands, R1 summands, which are linear form in this direction, and some bilinear forms here. So these elements may be non-zero. In the second direction, we have some R2 summands. So these elements may be non-zero. And also in the third direction, we have some R3 summands. So these elements in the box might be non-zero. But here we have a large part of the tensor, which is zero. And now, if we take this tensor and multiply so let's say this is R2 and R1, for example, and this is n minus R1. This would be, let's say, P1, Q1. This would be Q2, and this would be Q3. So we multiply each basis element here by epsilon to the power Q2, and here by epsilon minus R2. Epsilon Q1, epsilon minus R1. Epsilon Q3, epsilon minus R3. So these powers are chosen in the way that the matrices, the diagonal matrix, which have this form, epsilon Q1, epsilon minus R1, epsilon minus R3, has determinant 1. And we see that if R1, R2, and R3 are small enough, then by multiplying it in this way, we can multiply every element of a tensor which is non-zero by a positive power of epsilon. And this means that if we let epsilon go to 0, in the limit, we get a zero tensor. And this actually happens if R1 is less than, so if the tensor is in L times M times N, R1 is less than a third of its size, R2 is less than a third of its size, and R3 is less than a third of this size. So this means that if this decomposition has very low number of summands, well, not actually very low, there's constant number times the dimension, then the tensor is not semi-stable. And this gives us a lower bound on the slice rank of semi-stable tensor. So if a tensor is semi-stable, it must have large slice rank. So in numbers, so if T is semi-stable and it lies in CL times M times N, then the slice rank C of T is actually has actually the maximal possible value, which is the minimum of L1 over xi1, M1 over xi2, and 1 over xi3. And in this way, if we have this decomposition of a tensor into blocks and each block is semi-stable, we can get a lower bound on the slice rank of power of k. And we get an upper bound as previously just by using a slice decomposition of optimal size for each block. And we'll get the result that we want, this kind of optimization result. And this result over complex numbers is proven actually in the same way, except we use a different decomposition, which is related to representation theory of a general linear group. And then we can prove that the blocks that we get are semi-stable and their size is proportional, that is approximately governed by the entropies of some probability distributions. So I guess I can explain just a little bit about how can we use this kind to prove barriers on methods for matrix multiplication. So as I said, when we prove, when we construct algorithms for matrix multiplication, now we actually use some intermediate tensor, which has some nice algorithms and has some nice structure, which allows us to extract matrix multiplication from it. And if we have this kind of structure, then we have an upper bound on matrix multiplication exponent. Now, if you take any maps from tensors to real numbers, which have nice properties, as we discussed previously, so f t k and f of t is s and f of s if t is a restriction of s. Then from the first part of inequality, we get that f of matrix multiplication to the power of q is less than f of t. And it follows that q is less than log f of t over log of matrix multiplication. And from the second inequality, we get that g of t is less than g of e2 to the power of p. And it follows that p is actually greater than log g over log g of i2. And this sometimes gives us barriers on this fraction p over q, which gives us an upper bound. So p over q in this case is greater than log g over log f times log f of matrix multiplication over log g of i2. So here I used square matrix multiplication tensor 2, 2, 2. But in the same way, we can obtain barriers for rectangular matrix multiplication. So if we have some matrix multiplication of size n times n matrix times n times m matrix, and again, we have some intermediate tensor, which is used to obtain algorithms for this. And let's say this pk plus k. And again, we can do the same thing and say that our omega, our upper bound on omega, which is, so here omega is an exponent of rectangular matrix multiplication log mn. It's omega of p is the optimal complexity of such that n times n matrix and n times n to the p matrix can be multiplied using n to the omega operations. And in the same way, we can prove that if we use some intermediate tensor, we cannot prove any bounds, better than log g of t log f of t log f of matrix multiplication over log g of diagonal tensor. And these kinds of barriers were proven by Allman and Wasilewsky-Williams using slice rank for square matrix multiplication, and also by Christandel, Vrana, and Zuidam using their quantum functionals, which are also monotone. And we use weighted slice rank essentially. So we actually don't use weighted slice rank in the paper, which is on arXiv, because we first wrote the paper and used quantum functionals to prove this kind of barriers for rectangular matrix multiplication. And then reviewers said that probably we can do something like this with appropriate notion of weighted slice rank. So we thought that maybe we should try to actually get what he is saying. And now we can use this weighted slice rank as f, and as g we essentially use the size of the tensor. And for example, we can prove that the tensors used in the Kopia-Smith-Winograd algorithm cannot prove that n times n matrix multiplication and n times n 0.62, I believe, can be done in an optimal is in n square iterations. So that's one application of this weighted slice rank. We are actually hoping to use this weighted slice rank in some combinatorial applications, but so far we tried to do something with tensors which come from the sunflower conjecture, but so far we don't have it. And another application is to quantum entanglement. So if we have a quantum system, if we have three parties A, B, and C, and each of them has some quantum system which can interact with each other and can be entangled. So if the particle A can be in L possible states E1 up to EL orthogonal states, and it can also be in their superposition. And if particle B can be in M states, particle C can be in N states, then the state of this tripartite system is described by a tensor, because we have the states which are defined by EI, EJ, EK, and we also have all the possible superpositions of the state, somehow normalized, but essentially a state of a quantum system is described by a tensor. And one thing that we can do with this is we can use so-called SLOCC entanglement transformation, which means that each of the parties can use any operations on the particle which belongs to them. And they also can communicate classically. And the question is, if we have a given state between three parties, which other states we can get from this state? And the thing is exactly that if we have state phi, which can be transformed to psi, if and only if psi is a restriction of phi. This is for pure state. For mixed state, there is some other theory, but for now this is. And one thing that is actually somewhat practical, because this SLOCC transformation is that we can get one state from another with non-zero probability. Because if we measure something, with one probability we get one result, and with another probability we get some other result. And this S says stochastic, so with non-zero probability we get something. One case where we actually can have something not just with non-zero probability, but with non-negligible probability, is if you want to transform an entangled state between between three parties into an entangled state between just two parties. Then actually the rank of the entanglement between B and C is described by the slice rank weighted by 0, 1, 1. And our formula can be used to find the asymptotic transformation rate, which means that if we have many copies of a state phi, how much this bipartite entanglement can we get from this many copies is governed by this formula, which is maximum of minimum 2 to the h1, 2 to the h2. H1 and h2 are some two entropies which can be defined from this state. So yeah, any questions?
Colleagues?
I have a small question. Just on this slide. How does it go in the opposite direction? Because if you reduce phi to psi, then it might be arbitrary linear transformations, and we need unitaries somehow. How do you get from
so local operations mean that you can apply unitary transformation, and you also can apply measurement.
Oh, plus measurement. Yeah.
Measurement is yeah.
Measurement is allowed here. Yeah. Okay.
Yeah. Okay, then I think we can finish.
Yeah, I think no questions. So let's thank the speaker then. So, thanks very much. Edward, I think we can stop the recording.